Hi. Now, under certain circumstances, the binomial distribution, and here we have one where n is 40 and p is 0.5, takes on the look of a normal distribution. It doesn't always happen, but when it does, it just means that when we're doing certain calculations, which can often be tedious, they can be simplified by approximating the binomial distribution to a normal distribution. So what are these conditions that allow a binomial to approximate to a normal? Well, let's just keep p at 0.5 and start to reduce n. Keep looking at this number here and how the distribution changes. We'll start reducing it, okay, and you can see that the distribution still remains symmetrical. Let's just reduce it a bit more. We're down to n equals 12 and it still is symmetrical and takes on a normal distribution shape. So that seems fine when p is 0.5 despite changing the value of n. Let's see what happens when I change the p value. Let's say we change it to 0.2. As you can see, the shape of the distribution changes. In fact, this particular distribution is positively skewed. So what happens now if we start to increase n? As we increase n, you can see the shape is changing, and as n gets larger, it's starting to tend towards a normal distribution curve. Once we start to get to our value here, this is now at 100, you can see this looks pretty impressive. But it seemed to take quite a long while for that to happen. We needed quite a large n. Let's take this back now to a binomial again where n is 12 and p is 0.2. And this time let's start to change p. We know when it's 0.5 it's symmetrical, but let's make it close to 0.5. Let's say 0.4. The distribution changes. It's not normal yet, or it's not approximately a normal distribution, but as we start to increase n, let's see what happens. It starts to work towards a normal distribution, or the shape of a normal distribution, very quickly compared to when we were doing one just before. Remember, I did 0.2 here and I took n up to 100 before it really started looking quite like a normal distribution. So what tends to happen is that it approaches this shape quite quickly when p is close to 0.5 as we increase n. And this is what the conditions are essentially when we're looking at approximating a binomial distribution to a normal distribution. What we find is that when n is large and p is close to 0.5, then x is distributed like a normal distribution approximately. Now, the normal distribution has two parameters, the mean and the variance. And the mean for a binomial distribution was np, so we use that for the mean in the normal distribution. And the variance of a binomial distribution is given by npq. Remember, q is 1 minus p. Now this is fairly vague. How large is large and how close do we have to be to 0.5 for this approximation to work? Well, as a general rule of thumb, it is more convenient to use this rule. That is that when np is greater than 5 and nq is greater than 5, remember q is 1 minus p, then we can use this approximation. Now what I'd like to do now is do an example where I show you how we can use this approximation. Okay, well, what I've got here is that in a game the probability of a coin landing in a particular square is 0.4. So what is the probability that in 30 games the coin lands in the square fewer than 16 times? So if I was just doing this normally without any form of approximation, what I'd do anyway is define a random variable. I'd say let x be the random variable, number of times the coin lands in the square, where x is distributed binomially and n is 30 and the probability of success is 0.4. And if I was to try and work this out by calculation in the sense of just from the formula that we've got here, then the probability x is less than 16 would be equal to probability x is less than or equal to 15. And that would be working out probability x is 0 plus 1 and all the way up to 15. And that's a lot of calculations, as you can see here. But nonetheless, I've done it for you and it comes to 0.9029. So there's got to be a quicker way, and that's where this approximation comes in. Because if we were to look at the distribution for this binomial, then you can see I've outlined it here. It's got this normal distribution shape. And if we apply our rules that I showed you earlier on, that if we look at NP, let's just write it up here, NP is going to equal n being 30 multiplied by p, which is 0.4, we end up with 12, and 12 is a value greater than 5. So we see that NP is greater than 5. NQ, let's just work that out, NQ. Q is 1 minus p, so Q is going to be equal to 0.6. So that's 30 multiplied by 0.6, and that gives us 18, which again is clearly greater than 5. So with this general rule of thumb, we can see that we can approximate this to a normal distribution. So x is distributed normally, okay, with a mean, and that mean is always NP, and we've just worked it out, it's 12, okay. Then we need the variance, and the variance is NPQ. So let's just work out what NPQ is. So that's going to be 30 then for n multiplied by p, which is 0.4, multiplied by q, which is 0.6. And if we do that, that comes to 7.2. So the variance will be 7.2. So x is distributed normally with a mean of 12, variance 7.2, but approximately, so we better put that in, okay? I'll just say approx. And what I'll do is we'll just put a curve around that distribution, illustrating this normal distribution. So how do we go about working out the probability that x is less than 16? Well, to do this, we need to think of working out the area to the left of 16. But we're dealing with a discrete probability distribution and only approximating it to a normal distribution, which is continuous. So we've got spaces between these black lines. And to get around that, what we do is we imagine that rectangles fill those spaces. And these rectangles are of unit width. But can you see that part of the rectangle always sticks outside the curve and some of it is inside the curve, leaving us with little spaces where we've got some that leave us a little gap here, for instance, and then the other part is outside the curve. So we need to apply what we call a continuity correction to adjust for this kind of loss of area. And I'm assuming that you're familiar with continuity corrections. I'll talk briefly about it here, but if you click on the link that you'll see down here, then you can go directly to the tutorial that gives you information on continuity corrections. So we're looking at the probability being less than 16, and so we generally have got to think of this rectangle here, which I'll have to just highlight, okay, make it a bit larger. We're looking at 16, okay, and we've got its probability up through here, and we've got the rectangle drawn round the 16 of unit width. So we're trying to work out the probability of being less than 16, so we want the area to the left of it but not to include the 16. So what we do is we have part of the graph coming through like so, and the area that we want is to the left of 16 but doesn't include it, so we go up to the left hand side of this rectangle. And because the rectangle is unit width, this value here is at 15.5. This one would be at 16.5. So with our continuity correction, we approximate this to the probability that x is less than 15.5, okay, rather than 16. If we were looking for the probability x was less than or equal to 16, we would need to include the 16, so we would go all the way up to this side of the rectangle at 16.5. So if the question had said, what's the probability x less than or equal to 16, then with our continuity correction we would have said this is the probability x is less than 16.5. Okay, and we always have less than here, whatever we have over here. Okay, if it was less than or equal to, that is. Okay, well now we just carry on with applying the normal distribution. We need to get our standardized z value when we have an observed value of 15.5. So this is the same as the probability then that z is less than the observed value, 15.5, minus the mean, 12, all divided by the standard deviation, which is the square root then of 7.2, the variance there. And if you work this out, this works out to be a z value, a standardized z value then of 1.3043, and so on. And then if we look this up in the tables, you'll find that you get 0.9032, which to 2 decimal places is equal to 0.90 to 2 dp. Okay, 2 decimal places. Now, if you were to compare this to the actual answer was 0.9029. So there's not much in it, okay, for very little work. And obviously if you're doing this question, you wouldn't need to draw as much detail as I've got here at all, but just check out that NP is greater than 5, NQ is greater than 5, set up your normal distribution, your approximate normal distribution, do your continuity correction, and just use your tables to work out the corresponding probability. Okay? So I hope that's given you an idea. Don't forget, as I say, you can check out continuity corrections just by clicking on the link that you'll see down here. Okay?